Chapter 8, frequency response methods. So far the input signals that we were using, you had the impulse input. Actually, we did not really use impulse input, but you have the step input, you have the ramp input, you have a parabolic input, and you can say we had the impulse input as well. For the Laplace transform of impulse input is of course 1. So when you are discussing the frequency response of control systems, circuits, anything, frequency response means that you are changing the frequency of the input signal, and you are observing the signal at different spots in the system to see how the change of frequency is affecting two things, especially the magnitude of the signal anywhere in the system, especially the output, and the phase of the signal, again at the output or wherever you want to measure the phase of the signal. So when we are changing the frequency of the input, that means the input must have a frequency. And a sinusoidal signal is the signal that we use as a test signal, because we can change the frequency of the sinusoidal signal, and we can look at the response at different spots to see how the output is changing. Now, if our input is a sinusoidal signal, remember you will have transients, but transients, of course, they die. And the only output, sustained output that will be left if your input is a sinusoidal signal will be sinusoidal signal. Again, as I said, the magnitude may be different and the phase may be different with respect to the input signal, but it will still be a sinusoidal signal. Transients, of course, are going to die. So in this chapter, basically our test signal is a sinusoidal signal. We're going to change the frequency from 0 all the way to high frequency, and we are going to see how the output of the system is behaving. That is, at what frequencies the magnitude is high, the magnitude is low, what frequency the phase is, whatever the value of the phase is. So basically, anytime you are using frequency response, we are looking at the system from basically a filter point of view, that what frequency values can pass through the signal, pass through the system, and what frequency values will be stopped by the system. So every system, basically, it works as a filter. It can be operated over a range of frequencies, whether low frequencies, high frequencies, or band of frequencies. So every real system only works for a specific range of frequencies. So every real system, it acts as a filter, because anytime you're creating a filter, anytime you're creating a system, you will always have reactive components, whether it's in the electrical system or mechanical system. You will always have reactive components that can store energy and release energy. And the performance of those components depends upon the frequency of the input signal. So therefore, it is important to look at the frequency response of the system, of the control system, to decide that over which frequencies, if your input signal is sinusoid, that is, over which frequencies you can use this system, and which frequencies the output will be extremely low. And of course, you can look at the phase as well if you have a specific application related to the phase response of the system. So that's the whole idea of studying the frequency response of control systems. Now, when we are studying frequency response, our Laplace transform, which is sigma plus j omega. Anybody remember what is sigma and what is j omega? What is sigma? What does sigma represent? On the S plane, sigma is the real value. J omega is the imaginary axis.
Thank you.
What is the effect of sigma? What is the effect of sigma on the output of the system? Come on, guys. It's not a trick question. It's a simple question.
So, what was the question? The internet here is really bad. It kind of not. You said sigma effect on the output.
What is the effect of sigma on the output of the system? Oh, is my voice cutting off or something?
The school. I'm at the school, and the internet is really bad.
Oh, the internet is horrible at this school, and they keep sending messages every day that we are experiencing system degradation. Anyways, yeah. So my question was, what is the effect of sigma on the output of the system? We've been discussing this throughout this course.
Doesn't the sigma indicate the stability?
No. So if you have a root, let's say S is equal to 3 plus minus J5, then what will be the
magnitude?
What will be the effect of 3? What will be the effect of 5? J5. Guys, anyone?
The 3 would be the magnitude, while the 5 is the.
What do you mean magnitude? I'm talking about what will be the effect on the signal if you have these two complex conjugate root, 3 plus minus J5, as poles. Let's say poles. If you have these poles. Anyone else? Take a shot at least.
Is sigma like the left or the right shift? Like it's almost like a phase shift, but not exactly. It's like
no, sigma is not shift. Sigma.
Coefficient?
Say it again.
The dampening?
Damping. Yeah. Yep. Who says damping? Edmund, you said damping?
Yes, sir.
Yep. That's right. Sigma is damping. It's the exponential decay or exponential increase based on where the root is located. That's the real part. That correspond to e to the power negative 3t or e to the power positive 3t based upon where this is located. If it is located like this root is located in the right-hand plane, so this will correspond to e to the power 3t, so it will be exponentially increasing. Now, what is the effect of this? J5. So Edmund is right. That's the damp that represent damping of the system. How fast or how slow a system is going to damp out. What about J5? Anyone? You guys did the inverse Laplace and calculated the time domain response and everything. If you have these two poles, how the response is going to look like?
The frequency?
Frequency of what? You're right. Frequency of what?
Of the imaginary part?
Well, yeah, I mean, it is imaginary, but this corresponds to the frequency of?
Angular frequency?
Say it again.
Angular frequency?
Well, I mean, it is angular frequency, omega, but what does this frequency, like how the signal is going to use this frequency? I don't know if that makes sense or not. How signal is going to use this frequency? Where it is represented in the signal that you're going to get in time domain, let's say, because 3t or negative 3t represent damping, exponentially decay or exponentially increase of the signal. Now that frequency, angular frequency, you're right, it is an angular frequency, 5 radian per second. This frequency corresponds to what part of the signal? Which part has this frequency? As circuits, you did that in circuits, we are discussing it in this course as well. There's
a steady state.
Well, this is a transient part, by the way. It's not a steady state part. If you have only J5, then you're gonna have a steady state. What? This corresponds to the sinusoidal signal. Remember, if you have a signal sigma plus j omega, if you convert this into time domain, if these are the two poles of your control of the output, then when you convert it into time domain, you're gonna get a signal e to the power 3 cosine of 5t and whatever your magnitude, 5t plus theta. So this is the sinusoidal frequency, and the response of this is going to be an exponentially increasing sinusoid, and the frequency of the sinusoid is going to be 5 radian per second. And if 3 is negative, then it's going to be exponentially decreasing response. So this is, we discussed that. I've been discussing it in multiple chapters, by the way. Now, if you don't have 3 or negative 3, that means there is no damping. So you will have only cosine of 5. So that's going to be a sustained frequency, sustained sinusoid. But if you do have damping, that the sinusoid is either going to be increasing in size because of this, or decreasing in size because of negative 3 or negative 2 or whatever is there. So if you ignore sigma, then S is simply j omega, and that represents that you are dealing with only sinusoidal signals, assuming your transients are pretty much gone, or your test signal is a sinusoidal signal. Now remember, even in test, when your test signal is a sinusoidal signal, you will still have some transients before you get to the steady state. But as I said, the steady state signal is going to be a sinusoidal signal with the frequency S is equal to j omega. So that's what we are using here. S is equal to j omega instead of S is equal to sigma plus j omega when we observe the frequency response due to a sinusoidal signal. Sinusoidal signal with different frequencies, amplitude are readily available. Thus, the experimental determination of the frequency response of the signal can be easily accomplished. So these are some of the advantages of sinusoidal signal as test signals when we perform the frequency analysis. Design of the system in frequency domain provide the designer with response of the system to undesired noise and disturbances. Will control bandwidth of the system as well as some measure of the response of the system to be undesired noise and disturbances. So when you are playing with the frequency response, you can set the parameters such that your system is going to work on a specific band of frequencies, like we were discussing this morning also in DSP. You can have a band of frequencies at the low side. The system is going to act as a low pass filter. High side is going to act as a high pass filter, or most of the time, most of the systems are band pass. Well, they act as a band pass filter. They're not band pass filters, but they act as a band pass filters, such that they work over a band of frequencies. Now, since we are dealing with j omega, S is equal to j omega, which is a complex quantity. As S is a complex quantity, we know S is equal to sigma plus j omega, complex quantity. Therefore, anytime you have a transfer function and you're putting S is equal to j omega, then you will have a magnitude of the transfer function right here and phase of the transfer function that will change when you are changing the omega. And that's what we want to see. How the magnitude is changing when you're changing the omega, how the phase is changing when we're changing the omega. So in effect, we are using in this course, in this chapter, we are using Fourier transform, because Fourier transform is derived from Laplace transform when S is equal to j omega. Again, I'm not asking you to do any derivation, like we didn't do any derivation of Laplace transform. We just use tables. In this case, we are not even using tables. We're just going to be writing down the transfer function in terms of j omega, and then we will be calculating phase response and magnitude response, and then plotting them to see the frequency response curves. But just for the sake of putting it in the slide, so you know the similarities between Laplace transform and Fourier transform. As I said, Fourier transform comes from Laplace when S is equal to j omega. So as you can see, the Laplace transform equation that we discussed earlier in this chapter, how to calculate a Laplace transform of a function f of t from 0 to infinity, ft e to the power negative st dt, and the inverse Laplace transform to go back from f of s to f of t. The formula is this. Again, we have not used the formula, and we will not going to be using the formula to calculate anything, but just to see the similarities. For Fourier transform, when you're calculating Fourier transform of a function f of t, again, you go ahead and replace s by j omega. So f of t e to the power negative j omega t dt. It should be 0 over here if it is a single-sided Fourier transform. This is double-sided Fourier transform. This is single-sided Laplace transform. So for 0 over here, there should be a 0 over here as well. And inverse Fourier transform, again, similar to this, 1 over 2 pi negative infinity to infinity f omega e to the power j omega t t omega. All right, what type of different plots do we have to observe the frequencies? Actually, we'll be discussing 3 plots, but we're going to be spending most of the time on one type of plots, which are Bode plots, because those are approximate plots, but give us really good representation of the frequency response of the system. Every plot can be plotted, of course, using MATLAB. But again, understanding is important, especially Bode plot, because Bode plot are very easy to draw with a free hand, basically. But again, understanding as how we are doing the Bode plot is important, so we're going to discuss that. Here, basically, we are showing you that you have a transfer function, GS, call it process, call it whatever you want. And when you put S is equal to j omega, then the transfer function can be written as a complex number, real part of g omega and complex part of gj omega. So real part of gj omega, and complex part, imaginary part is x omega is imaginary part of g of j omega. So this is rectangular, basically rectangular points. So if you have gj omega, and this is your real axis, and this is your imaginary axis, then of course you can, plot points which will be real versus imaginary, and that type of plot is called the polar plot. You can also do polar plot based on what is the length of this vector and at what angle this vector is. And then we can keep creating this. At this angle, you have this value. At this angle, you have this value. And that can also lead to a polar plot. So this plot is real versus imaginary of, or if you're plotting the output or transfer function, whatever, but the real part of the transfer function versus imaginary part of the transfer function, or magnitude of the transfer function versus phase of the transfer function, at what phase that magnitude exists. And the other plot is magnitude of the transfer function versus omega, and phase of the transfer function versus omega. So there are 2 plots. One plot is magnitude versus frequency and phase versus frequency. And the other plot, which is the polar plot, is the magnitude at whatever phase, you put a point and then connect all the points to call it a polar plot, which is the same as real part versus imaginary part, where they are located in the S-plane. Let's look at an example. Plot the polar frequency plot for the transfer function of the following RC filter. So you have an RC filter, something that you must have discussed in circuit analysis as well. Okay, first we can write the equation and then I'm going to ask you a question. Okay, So remember, S is j omega. So the input is V1 j omega, which is a sinusoidal signal. And the output is V2 j omega, which will also be a sinusoidal signal at the steady state. R does not change with the frequency, or it does, but we don't consider it to be changing with the frequency. And then, of course, you have the reactance of capacitor. Anybody remember what is the expression for the reactance of capacitor?
1 over negative j omega c.
1 over what?
Negative j omega c.
No, not negative j.
XG?
1 over j omega c, not negative j omega c. Negative j is basically when j comes in the numerator, then it becomes negative j. But it's 1 over j omega c. Okay, so who is going to tell me? We are writing the transfer function of the system. That means output over input. That's the transfer function. H of j omega is V2 j omega over V1 j omega. And I don't know how many times I have done this in different classes, or we have done this in different classes. So who's going to tell me what will be the expression of the transfer function? And how are we going to get that expression? Andre, I cannot hear you. The college internet is just messed up real bad. I don't know what they're doing.
Could I use a voltage divider?
Okay, that's good. Voltage divider. So what will be the equation?
It would be V1 times 1 over j omega c divided by 1 over j omega c plus r.
All right. So first we write the equation as R over R plus, X over R plus X. Of course, voltage division means that V2 is equal to X over R plus X times V1 j omega using voltage division. And now X is my 1 over j omega c, R plus 1 over j omega c. So H of j omega is simply 1 over 1 plus j omega R c. All right, 2 ways to plot the polar frequency plot, as I mentioned. One way is you're plotting real part of this equation versus imaginary part of this equation on the complex plane. And the other way is you calculate the magnitude of this and phase of this. And as you're changing the frequency, you plot a point or the line for the magnitude for whatever corresponding angle is there. And both will be same. Both will be called polar plot. So let me ask you this now. Again, we have complex number. And let's see who can answer the question. So first, easy question. What is the magnitude of this?
One.
Okay, I think you cut off or something. One. Anybody else except Andre? Andre's been answering, and Edmund has been answering. Catherine answered some, Nicola answered some, but many of you are quiet. So either I will call your name or start participating, please. What is the magnitude expression for this? I know how many times did we do that in signal processing, in this class, and other classes, in circuit analysis. It's a complex number written there. I want to calculate the magnitude. What will be the expression that I will be using to calculate the magnitude?
1 over square root 1 plus omega over omega 1 squared.
Omega over omega, where's omega 1?
That's the part I don't really remember.
I'm asking you this equation. I know what is omega 1.
Okay.
Just asking you for this equation.
Oh,
We'll come back to omega 1 in a little bit. But from this equation, what will be the magnitude?
I'm not sure. I'm not sure.
What? I mean, okay, well, you've done the. So again, complex number. You don't even memorize these. Remember, guys, the complex numbers. The rules don't change. How to calculate magnitude of a complex number? How to calculate phase? The rules are the same, and I don't understand why every time you see a complex number, it just becomes so difficult that you cannot figure out what is the expression to calculate magnitude or phase. I know how many times you guys have done that. Or should I call a name? I mean, Jasmine, you should know. Come on. I know you know. Let me know, Jasmine.
Sorry, I don't remember.
You don't remember how to do A plus JB, magnitude of that? Didn't we do it in TSP as well many times? Of course, remember, most of the time we use the absolute function or phase angle. But before we use that, we discussed that, the complex numbers.
Is it 1 plus omega squared?
Only omega squared? What is the imaginary part?
Isn't omega RC?
So what will be the magnitude?
Would be omega RC squared.
Omega RC squared. Very good. A square plus B square, square root of that. A square plus B square, magnitude of a complex number. If it is given in a fraction, then magnitude of the numerator divided by magnitude of the denominator. That's the magnitude if the number is given in fraction as a complex number. Guys, please do not forget these things. These are important, easy, and not sure why everyone find them so hard. All right, go to the phase. What is the phase of the complex number? Again, I have 4 lectures on the complex number. Please, this is like 30-minute lecture each. Find some time, watch those lectures. I can guarantee they're gonna help you a lot. And they're on YouTube. I don't know if I put links in your course section or not, but just Google my name, they're gonna come up. I created it specifically for our program or students because this is the issue in every class. So if you watch those lectures, it starts with the basics of complex numbers, arithmetic of complex numbers, second lecture. The third is like this type of circuits, how you can do these simple circuits using complex number. And then the fourth is use of MATLAB, which we've been using for complex numbers. So how to use MATLAB for complex number. Please at least watch the first 2 because this is from first 2 actually. All right, phase. How do you calculate phase of this complex expression? Who's going to tell me that?
Is it negative arctan of WRC?
That is correct. So tell me generically, in general, how do you calculate phase of a complex number which is given in fraction?
Can you just solve it, convert it to polar, and then take the angle?
Well, that's what I'm asking. How are you going to write it down as a phase? We are converting into polar. This is the polar form, the magnitude and the angle. Angle, that's the polar. That's the polar form. This is the rectangular form.
You find the phase of the numerator and then you subtract the phase of the denominator.
Bingo, that's what I was looking for. That answer I was looking for. Phase of the numerator minus phase of the denominator. Phase of the numerator minus phase of the denominator. Now, what is the phase of the numerator here?
Uh, 90.
No.
It's a negative 90.
No. This is your complex plane, right? You have real numbers here. You have negative real numbers here. You have imaginary numbers here. You have negative imaginary numbers here. where this number is located on the real axis.
0.
1. 0. Because it is located on the positive real axis, it's 0. The phase of the numerator is 0. What is the phase of the denominator? Again, arctan. Imaginary part over real part. So only the magnitude, not the j value. Y over x. So omega RC over 1. So negative arctan omega RC. And I think Jasmine, that's what you told me earlier. Or somebody, and that's what Jasmine or Catherine. Yes. So again, don't memorize these things. Just understand how complex number work. I mean, irrespective of what is given. So Catherine, you were saying omega over omega 1. Basically, this can be written as 1 over 1 plus j omega over 1 over RC. And this is what you are calling omega 1, which is basically your cutoff frequency of the filter. Omega 1, omega C, whatever you want to call it. So you memorize that expression. And again, you're supposed to memorize these things. You just whatever expression is given to you, you use that expression. So this is the magnitude, this is the phase. All right, next question. Again, this is something, as I said, I discussed in my first, I believe in my first lecture on complex numbers that I have on YouTube. All right, second question. And I know it's taking a little bit long, but it's okay, I guess. What is the real part and imaginary part? If I want to divide this into A plus JB, I'm going to do that. A is my real part, B is my imaginary part. If I want to represent this number as A plus JB, how I'm going to do that?
You multiply the complex.
Multiply with complex what?
Conjugate.
Yep, that is correct. You multiply denominator and numerator by complex conjugate. So your numerator is 1 minus j omega RC. All right, who's going to tell me what will be the denominator? Let's say. And what will be the denominator of this?
1 plus g omega RC.
1 plus what? 1 plus?
1 plus g omega RC.
1 plus j omega RC?
Mm-hmm.
When I multiply this and this, I'm going to get this?
It's going to be if you multiply, it's going to be j omega RC.
So you're asking me to write this again? When I multiply this and this?
If you multiply, it's going to be minus. It's going to be minus in anyway.
So what will be the result? I'm asking you what will be the result.
Okay, is 1 minus j omega RC.
So when I multiply these
or square, this is going to be squared. When you multiply, it's going to be squared. It's going to be omega or omega or C.
So you're saying 1 minus omega j omega RC squared?
Yes.
A Star Wars Lego at the calendar.
What?
1 minus omega RC squared?
Yeah.
So
picking him, listen. He's laughing right now.
No, not 1 minus omega RC squared. You guys are forgetting to multiply j. What is j squared?
Oh, so plus omega RC squared.
Plus omega squared, yes.
This guy, we literally in class today, like the teacher was telling me how to break, and every single student in the class is like, "Oh my god!"
Hey, you're on.
Well, don't
He's like special needs or some shit. you know?
Edmund, mute yourself.
you're on speaker.
Edmund,
sorry.
Yeah, no, mute yourself before you start cursing me. All right. Again, guys, I don't want to go into this the math, but nobody remember anything, so it's hard. Okay, so what is the real part of this? What is the real part of this? Anyone? What is A for this?
Is 1 is 1.
Yes. 1 what?
Okay, it's gonna be 1 plus omega or c.
1 plus omega RC?
The real pi is 1. That's all. That's what I know.
What is the real part of this expression? That's what I'm asking.
One over 1 plus RC squared.
1 over 1 plus omega RC squared. All right, good. What is the imaginary part of h of j omega?
Negative j omega.
Not j,
over...
just the magnitude. Negative omega RC over 1 plus omega RC squared. You can put j if you want. That's imaginary part. That is correct. Imaginary part is negative j. So now when you're plotting a polar plot, as I mentioned, you either go and plot real part versus imaginary part on the complex plane, or you plot magnitude for each angle, of course, when you're changing omega. So if you plot this for different values of omega, if you plot this for different values of omega, this is your complex plane. And this is your real axis, your imaginary axis. Negative imaginary. Okay, if I go back and we discuss omega goes from 0 to infinity, let's say. So at omega is equal to 0, what will be the value of the real part? And what will be the value of the imaginary part?
Omega 0 real be.
Okay, so real part is going to be 1, imaginary part is going to be 0. Or if we look at this, omega 0, magnitude is 1, and the phase is 0 degrees. Omega 0 or tan of 0 is 0. So we have, let's grab another color. We have 1 when omega is equal to 0. Real 1, imaginary 0, or magnitude 1 at the phase of 0. All right, when omega tends to infinity, very large value, then what we're going to have? You're taking a limit of omega going to infinity. Real is going to be 0. And imaginary, you have to use, since it's going to be infinity over infinity, then you will have to use the rule that you have to take you have to differentiate both numerator and denominator with respect to omega, and then apply the limit. It's easier just to look at this one actually. So your magnitude when omega tends to infinity Magnitude is going to be 0 because your denominator is going to be infinity or going towards infinity. And your phase is going to be what? If omega is a very large number, negative arctan of a very large number, what will be your phase? What will be negative arctan? Arctan of a very large number is going to give you 90. You have a negative sign over here. That means negative 90. So at negative 90, you have the magnitude 0. Omega tends to infinity. So if you're changing the frequency, omega is increasing from 0 to infinity. Your plot is going to move from 1 to 0. And it's going to be a semicircle actually when you plot it. Something like that.
Does it go back to the origin? I thought it went to negative 90.
0 minus arctan of omega RC. Negative 90 because of this negative sign. Because arctan of a very large number gives you 90 degrees. And this negative sign is going to make it negative 90 degrees. If there won't be any negative sign, then it's going to be positive 90 degrees.
Yeah, so that means it goes back to the origin if it's towards infinity?
So if omega is increasing its value, then it's going to start at 1, which is omega 0, and then it's going to move towards origin at omega is equal to infinity or very close to infinity. The value of magnitude is going to be 0, or the value of x and y, real and imaginary, both parts are going to be 0. So it's going to be at origin. Check any other value. Let's say omega is, we were taking omega 1, which is 1 over RC. If omega is 1 over RC, what will be the magnitude? Omega is 1 over RC. The magnitude is going to be what?
Well, if omega is what?
1 over RC, which is the cutoff frequency. So at cutoff frequency, what will be the magnitude? Or what will be the real value or imaginary value, whatever you want to look at. It's easy to do magnitude and phase. When omega is 1 over RC, what is the value of the magnitude?
Should be 1.
This should be 1, but the magnitude is going to be 1 over square root of 1 plus 1. 1 over square root of 2. Right?
Yes, 1 over square root of 2.
And what will be the phase of at that point?
Negative.
Negative 45.
Negative 45, exactly right. So at negative 45 degrees, you have, so like right in the center, because you're going from negative, you're going from 0 to negative 90. So right at negative 45, the length of this is going to be 1 over square root of 2. And this will be your point. So likewise, you can plot all the points and you will find kind of semicircle basically. And if omega is decreasing, then you're going to go from 0 to 1. Decreasing means or negative, sorry, not decreasing. Omega is negative, then you're going to go from 0 to 1 to complete the circle. And again, this can easily be plotted in MATLAB for any values of R and C. All you have to do is to plot the real part versus imaginary part, and you will get your result. Let's assume if your let's assume your R is 1 kilo ohm and your C is 1 microfarad. then your RC simply is R times C, which will be 1 milli, basically 1 exponent -3. So your H is simply, what is that? 1 over 1 plus j omega RC. Let's define omega first, sorry. So let's define omega goes from 0 to a very large number, let's say 1, 0, 0, 0, 0, let's say 10,000. And step size is 1. And H is 1 divided by 1 plus j omega RC. You can calculate the real part. Real of H is equal to real of H, and imaginary part. Imaginary of H is equal to image. Oops. I believe. No. What is the function to calculate real? Oh, it's lowercase, not uppercase. That's why. Is it the total real? Yeah, I think it's real. Yeah. And then all you have to do is to plot real versus imaginary. Plot real of H. Oops. Plot real of H versus imaginary H. And the plot is going to be, of course, we're going on 10,000. We're not going all the way up to infinity, otherwise it's going to hit 0. But you can see that started at 1, and then as omega is increasing, it is heading towards 0. So that's the polar plot, the first type of plots. The second type of plot is the one that we use actually very frequently, which is the plot of magnitude versus frequency and phase versus frequency in 2 separate plots. So your x-axis is frequency, whether it's in omega, angular frequency, or f, cyclic frequency. And you calculate the magnitude. Magnitude can be either the whatever value is that, or it can be in decibels if you do 20 log 10. And the phase is always going to be phase, and most of the time phase is in degrees instead of radians. So that's the second type of plot, that you plot the magnitude and the phase versus frequency. So I think that's the next problem. Let's do this and then take a break. Plot the magnitude and phase frequency plots for the transfer function of RC from that. So we'll just go and plot what we are doing here. So magnitude of H is absolute value of H, and phase of H is angle of H 180 divided by same thing that we do in signal processing as well. And then you can plot it versus frequency, f, 2 times pi times, omega over 2 pi, sorry. Omega divided by 2 times pi, cos omega is 2 pi f. And you can do one is going to be plot f comma magnitude of H. So this, now many times when we are plotting, what type of filter is this?
It's a low pass filter.
It's a low pass filter, exactly. It's a low pass filter. Now, many times when we are plotting, and we're going to do the Bode plot in a little bit, the x-axis we take in logarithmic scale, such that each the x-axis is divided into 10-fold of frequencies. So going from 1 hertz to 10 hertz to 100 hertz to 1000 hertz, but each 10-fold has the same width. Why do we do that? Because, for example, low pass filter, most of the frequencies are at low side, but we are going to a very high frequency. So kind of it compressed all the values in the low side, because again, you have the high frequency and then it's just compressing the low frequencies or the magnitude of low frequency. So many times if your low pass filter cutoff frequencies, let's say 300, 400 hertz or whatever, then it is hard to see. If you're plotting for a very long time, it is hard to see what is the action that is happening at the low frequency. So most of the time, we take the x-axis to be in the logarithmic scale. And in MATLAB, that is semi-log x. So instead of using plot, if you do that, copy quicker to clipboard, let's go ahead and plot that. So this is, and then I'm going to show you the other plot as well, because we're going to be using that plot. So the next is, if you use semi-log x instead of plot, and then do f comma magnitude of h, then that's going to show you a nice low pass filter graph that shows you that it is all the frequencies are passed up to approximately 100 hertz, and then the filters start going down. So x-axis is always wise. If you're plotting filter response or frequency response, most of the time x-axis is taken in the logarithmic scale. And for the Bode plot that we're going to study, the y-axis or the magnitude is taken in decibels. So these are the magnitude response. Let's write this down quickly. Log axis and f in log axis. Yes.
Can you show again that semicolon function?
Semi-log x.
Semi-log, okay.
Right here. Why is sending me an error? Omitting non-positive data and log plot. Oh, because I'm taking f is equal to 0. Of course, when you take log of 0, it does not exist. That's why it's giving me error. But yeah, it's semi-log x. And you can also have semi-log y if you want to divide the y-axis into logarithmic scale, but it's semi-log x. And the error is coming because, of course, log of 0 does not exist. That's why log is coming. Usually we don't take, if we're using semi-log x, we don't use the 0. We start with a value just next to 0, basically, whatever you want to do, 0.1 or something. And likewise, you can do the phase plot as well using the angle. We already did the angle, and that is going to give you the phase plot as well. Okay, guys, what we're going to do, we're going to take a break, let's say about 15 minutes. And then once we are done, then once we come back, then we are going to start Bode plots and hopefully cover whatever is left in today in the lecture. And I think I may add something more, the second order Bode plot, that we can discuss next week. So let's meet at 6:55, maybe 6:55. All right, guys, we're gonna start back. So we are going to start the discussion of Bode plots. And Bode plots are the same as what we have over here. The magnitude versus frequency and phase versus frequency. We did not do the phase versus frequency, but you guys can do that, of course. But Bode plots are approximate plots. That is, this is the exact plot. For each value of omega or f, the corresponding value of the magnitude is calculated and, of course, plotted versus f or omega. Right over here. Bode plot are approximate. They give you, with very good proximity, how the shape of the response is going to look like. And many times you don't really need a computer to plot those. And that's the main reason that we use Bode plots, that it gives you the indication of the frequency response, or not indication, actually, it gives you how the frequency response is going to look like with very good proximity. In Bode plots, we plot gain of the system, or transfer function, whatever you want to call it, in decibels. So as you can see over here, Gj omega, or you call it Hj omega, whatever you want to call it, it's calculated in decibel, 20 log 10 of Gj omega. And the phase, of course, is simply the phase that we've been plotting. The difference is your x-axis is in logarithmic scale. As I just introduced you the logarithmic scale, so your horizontal axis or x-axis for both phase plot and the magnitude plot in decibel, there it is expressed in the logarithmic scale. So each tenfold of frequency will have the same spacing. As I said, it is an approximate plots. That means we'll have to do some approximations. So different conditions. If you have in the if you have a constant term in your transfer function, so let's say you have transfer function h of j omega 32 1 plus j omega over 100 over 1 plus j omega over 2000, whatever the transfer function is given to you, 1 plus j omega over 5000, let's say. Let's say we have a transfer function, something like that. Now, how this transfer function is, I'm writing, we're going to come back to that in a little bit when we do the examples. But you can have, of course, numerator will be zeros, denominator will be poles, and of course, you can have a constant value as well. Now, I'm showing you only single order zero and single order pole. It's not any power except one. But you can have more powers. You can have double order of any pole or any zero. And you can also have second order. So, square terms, s square plus 2 omega ns plus omega n square, like we discussed. That we're not going to discuss today, perhaps next week. It's a second order or Bode plot of second order system. So today what we are discussing is if you have a constant term, then when you calculate the log of that constant term, 20 log 10, that is just going to be a decibel value, a straight line at all the frequencies. It's not going to change with respect to the frequency. When you have a zero, like here we have 1 plus j omega over 100. When you have a zero and you calculate the magnitude of that, who's going to tell me? Same question. Who's going to tell me what will be the magnitude of this term? 1 plus j omega over 100. Should I call name or somebody want to tell me? What will be the magnitude of this?
The square root
Or excuse me, yeah, the square root of 1 squared plus omega j omega over 100 squared.
There's no j in magnitude, remember, only omega.
I apologize.
Yeah, omega over 100 square, yeah. Okay, so that's the magnitude. So observe how it is written. Bode plot of a 0 is square root of 1 plus omega over omega 1 square, which is the same thing as this. Omega 1, of course, here is 100, what we are taking, which is the cutoff frequency for that part. So when you take the 20 log 10 of this term, 20 log of this, then of course the power half is going to come here, the rule of logarithmic logarithm, and it's going to become 10 log 1 plus omega over omega 1 squared. Now we do the approximation, because remember, Bode plot is approximate plot. And what is the approximation? We assume if omega is less than omega 1. So if this omega is less than omega 1, we assume that this term is negligible. The second term is negligible. And you are left with 10 log of 1. And log of 1 is 0. So basically, your value of on the graph for this term is 0 as long as your frequency is lower than omega 1. So in this case, as long as your frequency is lower than 100 radian per second, then on the graph, you're going to mark it as a 0 line. The next approximation is, as soon as your frequency is going to increase beyond omega 1, you will assume that these terms become quite large as compared to 1, and we're going to ignore 1, basically. So you're going to have 10 log of omega 1 over omega 1 square. Again, 2 is going to come here, multiply 10. Then it's going to be 20 log of omega over omega 1. Now this term, 20 log of omega over omega 1, if I write this down, and I explore this term for different values of omega. Remember, we are using x-axis as logarithmic scale, so we are increasing the frequency every 10-fold. So going from, let's say, 0.1 radian per second or 0.1 hertz to 1 radian per second to 10 radian per second to 100 radian per second. So if I increase this frequency 10-fold with respect to omega 1. So let's say I have omega is equal to as long as omega is less than omega 1, it's 0 anyway. So I'm going to start it at greater than omega 1, when omega is greater than omega 1. So let's say omega is 10 omega 1, 10-fold of that. Omega 1 will be cancelled out, and I have 20 log 10 to the base 10 of 10. What will be 20 log to the base 10 of 10? Log of 10 to the base 10. Remember, when you're calculating log, what you're doing, you're taking this number is a power of this number. So 10 to the power 1 is 10. So log of 10 with the base 10 is 1. And you can check that, of course, if you forget your log. So log of 10 is 1. That's going to give you 20 decibel. That means when omega is 10 omega 1, 10 times omega 1, your value is 20 decibel. If I increase that 100 times omega 1, what will be my value? 100 means I have 20 log of 10 square, which will be 40 log of 10. And we know log of 10 is 1, so it's going to be 40 decibel. Likewise, if I increase 100 omega 1 or 1000 omega 1, it's going to be 60 decibel. Then 70 decibel, 80 decibel, whatever. So every time you increase the frequency by 10-fold, your value of your decibel value of 0 increase by 20 decibel. Magnitude will increase by 20 decibel for every 10-fold of frequency above omega 1. So we call it that this line has a slope of 20 decibel per decade of the frequency. Any question about this? Anything, if it is confusing, please ask me. What is this concept? Is that clear? Everyone is clear? If we increase the frequency every 10-fold, the slope of the line that you're drawing for this function, that slope of the line will be 20 decibel per decade. Every decade, it's going to increase by 20 decibel. So, if, for example, this one, omega over 100, up to 100, it's 0. After 100 radian per second, at 1000 radian per second, it will be 20 decibel. At 10,000 radian per second, it's going to be 40 decibel. At 100,000 radian per second, it's going to be 60 decibel. So the line slope is 20 decibel per decade, and it is increasing every decade of frequency is going to increase by 20 decibel. If Bode plot has a pole, this was 0. This is pole 1 over. So, for example, this is a pole 1 plus square root of 1 plus omega over 2000 square. And you take the log of this term. So 20 log to the base 10 of this term. So that's going to be 20 log 10 of 1 minus 20 log 10 of the denominator. So 20 log 10 of 1 is 0. 10 to the power 0 is 1. Which leaves us to negative 20 log of 1 plus omega over square. So that's going to be log 10 of 1 plus omega over omega 1 square, which is right here. Omega over omega 1, sorry, not a square. You can cancel this square power right here if you want. Or actually, don't cancel the square power. Bring that half like we did over here. Bring that half over here. It's going to become 10 log 1 plus omega over omega 1 square. And then this 2 is going to come here. And it's going to multiply by 10. That's going to be negative 20 log. So you have negative 20 log 1 plus omega over omega 1 for a pole. That is for the factor that is in the denominator. So it is same as this, except you have a negative sign, which means every 10-fold of frequency, the value of this factor is gonna drop by negative 20 decibel. Every 10-fold of frequency above omega 1. The value is gonna drop by negative 20 decibel. Like this one was increasing by 20 decibel, this one is gonna drop because of negative sign. So the slope of the line is gonna be negative 20 decibel per decade. Every 10-fold of the frequency, you're going to have a drop of negative 20 decibel above omega 1. Up to omega 1 is going to be 0. So a pole produces a constant value produces a constant line for all the values of omega. 20 log 10 of k. A 0 produces $20 dB per decade. A line which will be 0 up to omega 1, and then it's going to increase 10 omega 1, 100 omega 1 is going to increase by 20 decibel each time. The frequency is going to be multiplied by 10, a decade of frequency. And likewise, your pole is going to be 0 up to omega 1, and then it's going to decrease with the slope of negative 20 decibel per decade. And to create the Bode plot, basically you're going to add all the values of individual lines, and you're going to have a Bode plot. So when we do the example, you can understand better. Let me see what else do we have. All right. So if you have repeated roots, let me see. Let me maybe perhaps do an example and come back to this. Plot the magnitude Bode plot for the transfer function of the RC filter from example 8.1. Okay, so let's go ahead and do this first. So Bode plot of this function right here. H j omega 1 over 1 plus j omega RC. Then we're going to go back to the repeated roots. So I have h of j omega 1 over 1 plus j omega RC. And I can write this down as I wrote this down earlier, 1 plus j omega over omega 1, where omega 1 is 1 over RC, which we also called tau, which is the time constant of the circuit. So what will be the Bode plot of this? So your magnitude of h of j omega is, as we discussed earlier, 1 over 1 plus j 1 plus omega over omega 1 square, or simply 1 over the square root of 1 plus omega over omega 1 square. Magnitude in decibel is 20 log to the base 10 magnitude of h of j omega, which is 1 over square root of 1 plus omega over omega 1 square, which we can write, of course, 20 log 10 1 minus 20 log 10 log of a over b. Of course, it's log of a minus log of the square root of omega over omega 1 square. So when we are plotting the Bode plot, you have to plot for this, which will be 0. Log of 1 is 0 for all frequencies. And we have to plot for this, which is the pole, as we discussed earlier. So if we plot, let's say I plot here. H of j omega in decibel. And then this is my omega. And let's say I start at 0.1 or 1/10 of omega over omega, or 1/100th of omega over omega 1, 1/10 of omega over omega 1, omega over omega 1, or omega 1, sorry. So let's say this is my 0.01 omega 1, this is my 0.1 omega 1, this is my omega 1, 10 omega 1, 100 omega 1, 1000 omega 1. So I'm increasing the scale by a multiple of 10. The frequency is increasing every 10-fold. Now this one is 0 for all the values. What about this? Now remember, the rule is that as long as omega is less than omega 1, we're going to ignore omega over omega 1. So you're going to have negative 20 log 10 of 1. Negative 20 log 10 of 1. Log 10 of 1 is 0, of course. So until omega 1, until this point, my Bode plot value, or my value for this, is going to be 0. as omega 1 start increasing beyond, or as omega start increasing beyond omega 1, we will ignore 1. Then you will have 20 log 10 of square root of omega over omega 1 square. So square and square root will cancel each other. So simply you will have omega over omega 1 with the negative sign, of course. So up to omega 1 is 0, and then for each value, should be 10. 10 omega, 100 omega 1, 1000 omega 1, it's gonna drop by negative 20 decibel. So you have negative 20 decibel, you have negative 40 decibel, negative 60 decibel, and it will keep on going. So that will be the Bode plot of your low pass filter. And as you can see, it gives you an idea that how the response looks like. We have the same response. When we plot it right here, we got the same response. And this is the approximate response. So it gives you an idea that, and remember, this is decibel. The one that we plotted was not in decibel. If we plot this in decibel, then this plot, of course, is 1. So that's log of 1 is going to be 0. So that's going to start at 0. And then at whatever value that we chose for RC 1000 or something, that is going to be your, what value, what we chose, I forgot what. That value is going to be your omega 1 over RC. And that's where it is going to be the cutoff frequency. But for us, that value, up to that value for Bode plot, it's going to be 0. And after that value, it's going to stop dropping with negative 20 decibel per decade. So that's the Bode plot of this system, magnitude Bode plot of this system, the RC low pass filter. Any question that you may have? This is the simplest example, remember. But if you have any question, please go ahead and ask me. No questions? Derive the transfer function of the following circuit and draw its magnitude Bode plot. All right. Who's going to tell me how we're going to do first? What we're going to do first in this? What we're going to do first in this one?
Convert it to the frequency domain.
Convert everything into frequency domain. Excellent. So this will be V in J omega. R is not going to change. Capacitor is going to change. This will be XC1. This will be XC2. This will be V out J omega. And again, this will be the source ID J omega. And this will be Vx J omega, which will be the voltage across the resistor Rx. Okay, if I want to write down the transfer function of this H of J omega, which will be V out J omega over V in J omega. How I'm going to do that? Who's going to tell me? Look at the output. So how I can calculate this output?
Don't we need to find the dependence or the V of X first?
Well, yes, we do.
So on the left side of the circuit, you have a series. So you can use the voltage divider through V of X in order to find the V of X.
Yep, very good. But what I was referring to is V out over J omega Vx j omega and Vx j omega over V input. So we can use the chain rule, and Vx j omega will be cancelled out and you will be left with that. So we find Vx first and we can take the ratio of Vx over V input. So as Josh said, Vx j omega using ohms, using voltage division is going to be what? Who's going to tell me?
Shouldn't it just be the R of X, I believe, over top of all of your resistor, your capacitor, and R of X?
Rx over R1 Rx XC1 times V input j omega. Which will be 4K. Let me just read it, leave it right now. Actually. All right, so we're gonna take this Vx j omega, we're gonna plug it in over here, divided by 200. Now, how are we gonna find the output, V out?
Can you do a current divider and then use Ohm's law?
You can use current divider, yes, definitely. And then you can perform Ohm's law, definitely. That's the correct way. That is one of the ways, that correct way to do it. You can also use the combination of these two, equivalent. You can find equivalent of these two, and then just apply the Ohm's law. So that is going to be 1 over XC2 plus 1 over R out. R out plus XC2 R out plus XC2, and that's gonna go in the denominator. R out XC2 over R out plus XC2. And then you can apply Ohm's law. So for this one, Vx j omega over V in j omega is Rx plus R1 plus Rx plus XC1. And from this, V out. Now, who's going to tell me what will be the expression for V out in terms of ZQ, let's say? Z equivalent.
It's the current times ZEQ.
You're forgetting a sign. Remember, V out is positive on top and negative at the bottom. The current is flowing in this direction. So it's going to be negative current times Z equivalent. Negative ID j omega. Because current is entering at the bottom, but you are taking the voltage positive with respect to top. Negative ID j omega times Z equivalent. This is Vx over 100, negative Vx over 200 times R naught XC2 over R naught plus XC2, which gives us V naught over Vx equals negative R naught XC2 over 200 R naught plus XC2. So when you put them next to each other, then you're going to get the complete transfer function, which will be this term times this term. Let's do that. It's a little longer. at least to go up to some point. So h of j omega is equal to h of j omega is equal to what do we have? Rx over R1 plus R2 plus XC1. Rx over R1 plus where is R2? That must be Rx actually. Yeah, that's Rx, not R2. R1 plus Rx plus XC1. And then I have negative R0 XC2 over 200 R0 plus XC2. So I'm going to put a negative sign here. R0 over XC2. R0 XC2 over 200 R0 plus XC2. R0 XC2 200 R0 plus XC2. And the negative sign is here. Negative sign equals okay, next let's write this down into factors, zeros and wholes. So negative Rx over let's just put down the value so we can do. So I have 4,000 this and I believe 1,000 this, so that's 5,000. 4,000 is Rx. So 4,000 over 5,000 times 5,000 plus XC2. So plus 1 over j omega C1 times R0 XC2 R0 is 5K and XC2 of course is 1 over j omega C2. What was it? 5K. So 5,000 over j omega C2 divided by 200 R out 5,000 plus 1 over j omega C2. All right, so negative 4,000 times 5,000. And I'm going to simplify this. J omega C1, so 5,000. J omega 5,000 C1 plus 1 j omega C1 times j omega C2 multiplied by this. So this will be cancelled out if I do that. So 5,000 over 200 times 5,000 j omega C2 plus 1. So it's shaping up as you can see. I can cancel this 2 with these 2 and 2 20s are 40. All right, what is omega C1, 5,000 omega C1 and all those things? We can look at that. We can calculate that. 20 times 5,000 into 5,000. So let's write this down. 20 times 5,000 squared. Negative sign. J omega C1. Let's see what is C1 and C2. C1 is 20 microfarad and C2 is 10 nanofarad. 20 microfarad and 10 nanofarad. So negative J. What was that? Forgot. 20 microfarad. That's going to be 20 micro. 20 exponent negative 6 times omega. That's the numerator. And the denominator is going to be, so we're going to write it down in terms of, let's see what is 5,000 times C1. 5,000 times C1 is 5,000 times 20 microfarad. C1 is 20 microfarad and C2 is, what is C1? C2 is 10 nanofarad. So 5,000 times C1 is 0.1. 5,000 times C1 is 0.1. So we're gonna have J 0.1 omega plus 1 and 5,000 times C2. Make sure it's 5,000. These two are 5,000 and the output resistance is 5,000 as well. So 5,000 times C2. 5,000 times C2. That's 5 exponent negative 5 or 50 exponent negative 6. So J 0.5 exponent negative 5 plus 1. All right, what we're going to do next? Remember, in which form we have to put it? We have to put it in the form of, as I was showing you earlier, right here. We have to put it in this form. Magnitude, zeros, poles, and we have to show the cutoff frequency. So j omega over the number, j omega over the number, j omega over the number. So if you look at this expression, the one that we have, of course, we can calculate 20 times 55,000 squared times 20 exponent negative 6. But first, we're going to put down negative j. And let's do that 20, so we don't have to write the whole thing. 20 times 5,000 squared times 20 exponent negative 6. 20 exponent negative 6. So 10,000. So negative j 10,000 omega over. I'm going to pull this outside 0. Oh, no, actually, I don't have to pull that outside. I'm going to write this down as 1 plus j omega over 10. 1 over 10 is going to be 0.1. And I'm going to write this down as 1 plus j, this is omega. And let's see what is 1 over 0.5 exponent negative 3. 1 divided by 0.5 exponent negative 5. That's what we got, right? No, we got 5 exponent negative 5, not 0.5. So this is 5 exponent negative 5. Let me fix this. 5 exponent negative 5. That's going to be 1 over 5 exponent negative 5 when we are putting it. 20,000. So now you see the shape of this. I have constant value, 10,000. I have negative j omega. So I can write this down as 10,000, 0 minus j omega over 1. Not 1 minus, but j omega over 1, or you can write down negative j omega, whatever you want to write down. Over 1 plus j omega over 10. 1 plus j omega over 20,000. So that's a simplification. It's a little complicated simplification, as you can see, but not that bad. I mean, you can still do that if you have to. The point is to bring it in the shape of constant 0, another 0 as a product divided by a pole, product of all the poles. So now this is h of j omega. If we write the magnitude of h of j omega, what that magnitude is going to be from this expression, who is going to tell me what will be the magnitude of that? What will be the magnitude of that expression?
It is the magnitude of the numerator divided by the magnitude of the denominator.
All right. So what is the magnitude of the numerator?
1,000.
1,000. Magnitude of this factor was, what is the magnitude of this factor?
It would be 0 square plus omega over 1 square, so omega squared under the square root.
So simply omega.
Yeah.
Right. Negative j. Remember, negative j omega. The magnitude of that is simply omega. What is the phase of that?
90.
Negative 90.
Negative 90.
Negative j. Negative j represent negative 90. So if you're writing it in terms of polar form, that's omega angle negative 90 degrees. So omega is the magnitude, negative 90 is the phase. So the magnitude of this is simply omega. Omega. All right. Denominator. What is the magnitude of the denominator?
So do we need to FOIL it before?
Well, you have to take the magnitude of each number, basically.
So 1 square plus
1 plus omega over 10 square.
Yeah.
And 1 plus omega over, what was it, 20,000? 20,000. 20,000 square. That is the magnitude of that, the transfer function of the circuit or system. So now when you convert this magnitude into decibels, then what you're going to get? 20 log 10 of 1,000. Plus, because of course these are products. So when you're taking the log of product, it will become addition. Omega. Minus and another minus. Now, who didn't get this expression? As how did I apply the log on that and wrote that expression? Is that clear?
Could you explain that again one more time, please? I'm sorry.
So how did I write this expression or this expression?
The bottom expression in
Bottom
decibels.
expression. So we are taking the we're converting this into decibel. So 20 log to the base 10 of the magnitude. So when you apply the log function, remember, if you have product, it becomes addition. If you have division, it becomes subtraction. So you go, and that's a good thing with taking log, because your whole thing become addition or subtraction. So you go 20 log of 1000, and then the product becomes addition, 20 log of omega, and the denominator becomes subtraction, minus 20 log of this factor, minus 20 log of this factor.
Thank you, sir.
Yeah. Again, if you remember your log rules, A times B over C times D, that's going to be log of A plus log of B minus log of C minus log of D. Or you can do minus log of C times D, and then that's going to become minus log of C plus log of D. And since there's a negative outside, it's going to become negative log of C minus log of D. So that's how we wrote this. Now, remember, each term has to be plotted separately, and then we're going to add all of them together. So the first term is simply 20 log 10 of 1000. 10 to the power 3 is 1000. So it's going to be 20 times 3. So that's going to be 60, the first term. Second term, we're just going to keep it like that. Third term, we're going to keep it like that. And we're going to apply the approximation on the third term. And we're going to apply the approximation on the fourth term. So let's draw. Do I have? Go ahead and insert. Insert on the slide. Now I have, let me put it on the right side actually. Omega h of j omega and decibel. Okay, so the first thing is 60 decibel for everything. So I'm going to put a 60 decibel. I'm going to divide it into 20 decibel, 40 decibel, 60 decibel, 80 decibel, negative 20 decibel, negative 40 decibel, negative 60 decibel, 80 decibel, so on and so forth. And then I can start at 1 radian per second, 10, 100, 1000, exponent 4, 1 exponent 5, 1 exponent 6. So I divided the x-axis, or I plotted the x-axis as a logarithmic scale, semi-log x. So the first thing is 60 decibel that we have. So I'm gonna use different colors. I'm gonna make a dotted line at 60 decibel for all frequencies. That's my first term. My second term is 20 log to the base 10 of omega. Okay, now if omega is 1, then log to the base 10 of 1 is 0. If omega is 10, that's going to be log of 10 will be 1. 20 times 1 is 1. Omega is 100. It's going to be 40. Omega is 1000. It's going to be 60. So it's going to start here. Let's see this. It's going to start at 0, at 1. And then at 10 is going to be 20, 40, 60, and then it will keep on increasing. So that is 20 log 10 of omega. It is increasing with the slope of 20 decibel per decade. 20 dB per decade. You have to show the slope. So that's my second line. My third line is negative 20 log 10 of 1 plus omega over 10. Now, remember, we're going to apply the approximation. As long as omega is less than 10, this is going to be 0. When omega exceeds 10, for every 10-fold of frequency is going to decrease by negative 20 decibel per decade. So we're going to go to 10. Use light blue. We're going to go to 10, which is 0. And then for after 10, we're going to decrease. And the slope of this is negative 20 decibel per decade. And that's my third term over here, negative 20 log 10 of this. So once again, as long as the frequency is less than 10 radian per second, we're going to ignore this term. So it's going to be negative 20 log 10 of 1, which will be 0. When the frequency exceeds 10 radian per second, then we're going to ignore 1. And it's going to become negative 20 log 10 of omega over 10. So if omega is 100, 100 over 10 is 2. 100 over 10 is 10. Then it's going to be log 10 of 10, which is 1. So negative 20 decibel at omega is equal to 100, negative 40 decibel at omega is equal to 1000, and so on and so forth. So at 100 is 20 decibel, at 1000 it is negative 40 decibel. What about the last one? Who's going to tell me, follow the similar fashion and tell me how I'm going to draw the line for the last one?
It'll be 0 until 20,000, and then it'd be a negative 20 per decade.
Right, exactly. So it's going to be 0 until 20,000. Let me put 20,000. This is 1,000, 10,000. So let's say 20,000 is here. 2 exponent 4, that's going to be 200,000, 2 million. We don't have to do all of this. So it's going to be, let's change the color. I don't know which one I choose, green maybe. So it's going to be 0 until 20,000, and that negative 20 decibel for 200,000, negative 40 decibel for 2 million. So I'm going to connect this. So now I have 4 different lines corresponding to 4 different parts of the equation. And observe, everyone is adding together, subtracting or adding, basically. So that's what we are going to do here. We are going to add all the lines together to give the Bode plot. This is not the Bode plot. This is part of the Bode plot. But we're going to add all of them together to give the Bode plot. So let's start. It's very easy. Let's go black then, or red rather. Let's do red. What is the red color right here? Okay, so you have 60 decibel, 0, and nothing. So it's going to start at 60 decibel. At 10, so this is increasing by 20 decibel per decade. So that means when it will be 10 radian per second, the 60 decibel would have increased to 80 decibel because you're adding this line into 60 decibel. So at 10 is gonna go to 80 decibel. Now what's going to happen after 10? This line is gonna start dropping by negative 20 decibel. That means this 20 decibel per decade and this negative 20 decibel per decade are going to cancel each other. That means your gain is going to become constant at 80 decibel because these two lines will start canceling each other. This is increasing by 20 decibel per decade. This is decreasing by negative 20 decibel per decade. So it's going to become constant at 80 decibel until when?
So 20,000.
Until it will hit 20,000 exactly. And when it will hit 20,000, then it's going to start decreasing by negative 20 decibel per decade because these two are canceling anyways. So they are gone. Only this line is left. So it's going to start dropping by 20 decibel per decade. So 2 exponent 4, 2 exponent 5 is going to be 60. It's going to start dropping by 20 decibel per decade. Whatever is that. I mean, of course, I'm drawing freehand. So you're going to write down this is 20 decibel per decade. And the slope of this line is negative 20 decibel per decade. So this red is your Bode plot for this system. But this Bode plot, remember, is coming from those 4 lines that we plotted corresponding to these 4 factors in the equation. Now, this problem again is a little complicated problem because, of course, you have to first solve the circuit and then put the values, then put the values in the required form. And then when you have the required form, of course, then do. Generally, if if the function is given to you, then it's not that complicated to see the factors and everything. But this is going to be the Bode plot of that. Can you plot it in MATLAB? Absolutely, you can plot it in MATLAB. Actually, there's a function in MATLAB, Bode, that can be used. But to understand it, remember, what do we have? Let's go to where is my, so this is my h of j omega. Let me just use that. So my Rx, the value of Rx was 1K, no, 4K, R1 is 1K. So let me enter these values first so that I can plot them easily. And if you have taken circuits with me, I don't think anyone anyone in the class has taken circuit with me, I think. That's what I do in circuits. I don't worry about solution part. I worry about analysis part. For solution, you can always do like I'm doing right now. So 4K, 4. So Rx is 4K, R1 is 1K, C is 20 microfarad, C1 is 20 microfarad. Let's see, what do I have? C2 is 10 nanofarad, C2 is 10 nanofarad, and R out is 5K. R out is 5K. Okay. So I put down all the values of my circuit that I have in the expression. Right over here. Where did it go? Right there. Okay, so let's go ahead and define the range of omega. Where is my MATLAB? So let's define the range of omega, and we are going. Let's see what we are going. We are going up to, like 2 million, 20 million or something. So from 1 to 20 million. So let's go ahead and define that. omega is equal to 1 to 20 million. I keep the step size to be 1, or we can do it 10, whatever. Step size of 10, so that we don't have, well, I still have a lot of points, but whatever. Okay. Might be a good idea to keep it 1, or let's plot it and then we can change, of course, omega always. So now I'm gonna go ahead and write down my xc1 is 1 over what? 1 over what? J omega c I times omega times c1. And my xc2 is I times omega times c2. So now I have everything here that I can use to write h of j omega. So my h is negative. Negative doesn't really matter because we're calculating magnitude, but for phase it does matter. Rx divided by R1 plus Rx plus xc1. Let's put it in parentheses. Times xc2 R0. So R0 times xc2. Put another parentheses. Divided by 200 times R out plus xc2. Do I have balance parentheses? Believe one is missing, right? Yeah, I think so. Starting here, this, and yeah, one is missing. Okay. So this is my h, and didn't get any error, so hopefully I wrote it correctly. Any question about this h, which is right in front of you in example 8.4 that we derived? Since we already have everything, that's why I wrote this. Although I could have just written this equation if you wanted, but I like to use variables most of the time. So that if I have to change anything, I can just go and change the value of that variable instead of numbers. Now, what should we do next? Who's going to tell me what should we do next to do the Bode plot?
We need our magnitude and
Calculate the magnitude first. So magnitude of h is the absolute value of h. But remember, we're not plotting just magnitude, we're plotting magnitude in decibel. So magnitude of h in dB is equal to 20 times log 10 of magnitude of h. So that's my magnitude in decibel. And now we're ready to plot our semi-log x rather, because we need the x-axis in logarithmic scale, semi-log x omega comma mag h in decibel. This is our plot, and this is our plot. Let's see. Where did it go? Okay. All right, we have it. Oh, hold on. Why it is? Maybe we have made some mistakes somewhere. So it's going up. Oh, did we make a? Maybe I made a mistake somewhere because it has to start at 60, not at some value. Let me see, what did I write down? Okay, 4 exponent 3, 1 exponent 3, 20, maybe my, yeah, I mean, the values Oh, that's nano. C2 is nano, I think, not micro. So let's go back. Right, C2 is nano, right?
Yeah, it was nano.
Yeah, C2 is 10 nanofarad. I put 20 something. So let's go back and fix that and then see if it will work. 10 micro, 10 nano. Okay, so let me go and fix that. 10 nanofarad. Exponent -9. Rest of them are same, I think, 5 kilo, 20 micro. Okay, so this we'll have to go again. Omega is okay. We have to calculate XC1 or XC2 rather, Khali. XC2, because we're changing C2 value. C1 is the same. And then H. And then magnitude of H. And then magnitude of H in this decibel. And then same log X. All right, this is better. But still, the value is not 60 decibel for some reason. I have to see why. Maybe we made a mistake somewhere when we were doing calculations. Okay. So we have we are starting at 1, right? Let me see where we are starting. Yeah, we are starting at 1. 1 and 10. So that should give 60 decibel. I mean, the shape is, you can see the shape is the right shape. But this value is not going up to 60. So maybe in our calculation, we made some mistake. And the constant value that we got is incorrect. But as you can see, the shape is what we are getting. This value seems like this value is not 60, most likely. This value is right here, 6.442. This value, it shows me 6.442 instead of 60 decibel. I have to go and check. Maybe I made a mistake when I was dividing and stuff, because there's just so many numbers over here. So I must have made some mistakes somewhere. But in any case, if, let's say, whatever mistake I made, if I carry that mistake all the way, and if my equation comes out to be this, then of course, according to this equation, the graph is going to be this. But since I made a mistake somewhere in calculation, then the constant value will not be 60 decibel. The constant value will be whatever you see over here, 6.23 or whatever you see over here. And the graph is going to look like this. So the point is, plotting with MATLAB, understand. So again, we are plotting using everything manually. And whatever shape you see, of course, it is plotted using all these values that we are entering. And you can also plot, and the shape, of course, you can see that the shape is pretty similar shape. It goes up to 10 to the power 1 right here. And then it becomes constant to that value, which is, what is this value? Let's see. Oops. Which is 26. So, 20 plus 6, 26 decibels. So it's increasing by 20 decibel per decade. Up to 10 to the power 1 becomes constant. And then it starts dropping down at 20,000, whatever, or 20,000 basically, to exponent 5. So it's going to start dropping down at 20,000 with 20 decibel per decade, negative 20 decibel per decade. So our constant value is not 60, it's the 6. So perhaps it was 100. Let's see. We put 1,000 over here. Perhaps it was not 1,000. Perhaps it was 100. That is going to give you. That's going to give you a 40. So anyways, but that's the issue. Basically, this constant value, maybe we did not calculate it correctly. Otherwise, the rest of it is pretty good. So this is how you can do Bode plot in MATLAB. It does not show you the individual lines. Observe, we are plotting it using individual lines and then adding all of them together. But when you plot it, it's just going to plot in MATLAB. It's just going to plot with that. Now let's try to use the Bode function. I forgot. I think I have used it. Bode. Okay. Let's see. Bode system. Okay. Let's define the system and then see how we plot it. So my system is transfer function. Let's see, where is it? All right, so yes, system is going to be numerator and denominator, and we have not multiplied it. So if we put s, generally it's given in s. So if we do, this is going to be j omega is going to be s, so it's going to be numerator. Go back. So I'm playing with it right now. Let's see if it works. So the numerator is going to be negative 1000 j omega is s. Negative 1000 comma 0, and the denominator is going to be, so j omega is s, remember, so 0.1 s plus 1, or we can 0. Plus 1, or we can just do s and take 0.1 out and then divide it by 1000, whichever way. Again, I have not used the Bode function, so I'm just gonna write down. I have 0.1 s, so, and then so let's create a polynomial from there. So if I take 0.1 as a common factor out, it's going to be s plus 10. So that's going to be negative 10. Negative 10 is one of the roots. And then for the second one, if I take 5 exponent negative 5 out, it's going to be 20,000 as one of the root, negative 20,000. Let's see if it will work. And since I took those two out, 0.1 and 5 exponent negative 5. So I will divide this thing by 0.1 times 5 exponent negative 5. Because I'm taking 0.1 out from here and 5 exponent negative 5 from here. All right, let's see if it works. Poly and transfer function. Oh, that square bracket is missing. What is that? 0, and this is, okay. Let's see. Too many inputs. Let's see where I'm making mistake. Okay, so this is your all right, so you have the root negative 10, you have the root negative 20,000. Why it is saying too many functions? Not 2,000. All right, so denominator. Let me see. See what this is gonna give me. So make a polynomial from these two roots. Oh, you have to put the roots in square bracket, that's why. You have to put roots square, yeah. Poly This is here, and then the roots are as omega. That should. All right, so poly, and then one more parentheses to end this function, transfer function. Let's see if this will work. Yeah, okay. And then Bode of system. Okay, here you go. The Bode of system, as you saw. See, it is coming out to be 60. Maybe we're making some mistake because our calculation is correct. That means. Oh, no, actually, no, we are we are plotting that. That's why. We're plotting this equation. That's why it's coming out to be 60. But we have made some mistake in the simplification of that equation. So again, Bode function, as you can see, it can plot the Bode plot, which matches with what we plotted for that equation. Remember, if the equation is incorrect, of course, that's a different story. This is the phase. We're going to discuss phase later. So Bode function is there, or you can just do it manually. Bode is much easier, of course, to use. Now remember, if I ask you to plot, of course, I will ask you to show the work. And then, of course, I'm not going to ask you to simplify the circuit and do it. Rather, the question is going to be something like that. So let's do this and then finish our class. Perhaps we will continue Bode plots next week as well, because we have to discuss the multiple roots, phase, and the second order system. So we're going to discuss that. But let's go ahead and plot this first. Oh, actually, it's the second root. So let's do this. Let me do it for single root right now. Or actually, let's do it for second root so you will understand it as well. So I'm going to write down. I'm going to write this down as G of S is equal to 200 S plus 1000. S plus 10, S plus 10, and S plus 100. Because I broke S plus 10 is square into S plus 10 and S plus 10. Okay, now further, I'm going to write this down as 200 over 1000, 1 plus S over 1000. Or 200 times 1000, sorry, not 1, because I'm gonna 200 times 1000, 1 plus S over 1000 divided by 10, 1 plus S over 10, another 10, 1 plus S over 10, and 100. 1 plus S over. Remember, how do we write it? Constant, any zeros, product of zeros in terms of 1 plus j omega over omega 1, j omega over omega 2. And poles, 1 plus j omega over omega 3 times j omega over omega 4, j omega over omega 5. That's a standard way to write the transfer function if you're plotting, if you're going for the Bode plot. Now S is j omega, remember. So first we can do 200 times 1000. So 10 times 100 is 1000. So that will cancel out 1000, 1000. And 200 over 10 is simply 20. So we're going to write down Gj omega is 20, 1 plus j omega over 1000 divided by 1 plus j omega over 10, 1 plus j omega over 10, and 1 plus j omega over 100. Magnitude. What will be the magnitude expression of this? 20? Who's going to tell me?
square root of 1 square.
Yeah, 1 square is just 1. Just say 1.
Plus, yeah, the second square.
So that's the magnitude. And go to the next page. Now you're going to put GJ omega in decibel. 20 log 10 of each. So I'm just going to skip that, but I'm going to write 20 log 10 of 20. Plus 20 log 10 of 1 plus omega over 1000. Minus 20 log 10 of square root of 1 plus omega over 10 square minus 20 log 10 of the same thing. And minus the last one, which was I think 1000. Yeah, 100. Minus 20 log 10 square root of 1 plus omega over 100. All right, now observe one thing. What did the square term do when you wrote it down in terms of logarithmic scale? Negative 20 log 10 of square root of 1 plus omega over 10 square minus 20 log 10 of square root of 1 over omega 10 square, which means I can add them together because they are the same terms. So anytime you have power in the log scale, you are adding 20 log terms. If it's zeros, power 2 power, you are adding 20 plus 20. If it is pole, you're adding negative 20, negative 20, negative 20, based on how many powers do you have. So you have 20 log 10 of 20 plus 20 log 10 of square root of 1 plus omega over 1000 square minus these two terms. I'm going to add them to 40 log 10 of 1 plus omega over 10 square. So these are 2 roots s plus 10 square and minus 20 log 10 of 1 plus omega over 100 square. So I have 4 terms. Basically, those 2 roots, the square power is going to be in the logarithmic scale is going to be added together, and it's going to become negative 40 log 10 of 1. So that's what happens to the power. Anytime you have a power of the same factor, basically you multiply 20 log by that power. So negative 20 log of this factor is going to become negative 40 log of that. If you have power 3, it's going to become negative 60 log of that, the magnitude. So we have negative 40 log 10 of the magnitude because the power is 2. If power would be 3, it's going to become negative 60 log 10. So this is what we have. So let's go ahead and 20 log of 20, that's going to be what? 20 times log 10 of 20. 26.021. So it's going to start at 26.021. 26. I'm just going to write down 26. Plus 20 log 10. So now what's going to happen with this factor? Who's going to tell me?
For the whole thing?
This one, this factor.
Oh, it's at 10,000 it'll start.
1,000. It's 1,000, right?
Oh, you just wrote 10,000.
1,000 is 1,000. No, I think I wrote 1,000. 3 zeros.
Yeah, you're right.
Yeah.
So,
So
at 1,000, it will increase 20 dB.
Okay, so up to 1,000 is going to be 0, and then after 1,000 is going to increase by 20 decibel per decade. So at 10,000 is going to be 40 decibel. At 100,000 is going to be 60 decibel. Okay, what's going to happen to the third term? Only the third term. Then we're going to add later. What's going to happen to the third term?
It'll be 0 until 10, and then decrease 40 dB per decade.
Exactly right. It's going to decrease by 40, not 20, 40 decibel per decade. And likewise, the last term
would be 0 until 100 and decrease 20 dB per decade.
20 dB per decade. Very good. Excellent. So this is what we have. So let's go ahead and plot that real quick. And then we can also, or you can check the plot using Bode function as well. So insert new slide, blank, draw. So I'm going to start at 1, 10, 100, 1,000, 10,000, 1 exponent 5, 1 exponent 6, 1 exponent 7. 20 decibel, 40 decibel, 60 decibel, H dB, negative 20, negative 40, negative 60, negative 80. So I have 26, the first one, mid is 30, so that 26 is going to be here somewhere. So I have 26 decibel for all frequencies. That's the constant value that I have. Actually, if it is 30, 26 will be like up somewhere, 6, whatever. That's my 26 decibel. The second I have is going to 1,000, and then it's going to increase 20 decibel per decade. So let's say 1,000 is 0, up to 1,000 is 0. Then it's going to increase 20 decibel per decade. So it's going to be 10,000 is going to be 20. So it's going to and then I have poles. It's going to go to 10 or 100. What is that?
We have one that goes to 10. That's a negative 40 dB, and the other is 100.
So the 10 is 40 decibels. So I'm going to take my 10, and then it's going to drop 40 decibels. So at 100, it's going to be negative 40. So the slope of this is going to be steeper as compared to negative 40 dB per decade. And the last one is going to 100, and it's going to drop to 20 decibel per decade. So it's going to go to 100, and it's going to drop to 20 decibels. So the slope is not going to be as sharp, of course, as the other one. Negative 20 decibel per decade. And then I'm going to add all of them together to produce my Bode plot. Red color. So I have 26 until 10 because there is no other line. Only the 26 is until 10. What's going to happen after 10?
Decrease by 40.
It's going to decrease by negative 40. So it's going to go 26 to 6, and then 6 to what, 14, right? Negative 14. Or so 26 minus 40. Negative 16, right? Negative 16 plus 40 is 26. Or am I correct or no?
Negative 14.
Negative 14? Okay, so negative 14. So that's going to be negative 14. And that is at 100 decibel. And then negative 34. 30 and 34. That's going to be, no, not 34. Negative 14 plus negative 54. Negative 54 is going to be at, so this is at 10, so 1000. That's going to be 1000. It's going to start dropping. Let me do it first like this, and then I'm going to add it. And it's going to go up to what point? I moved actually too much. It's going to go up to which value?
Just to the 100. It should
just to the 100. Yeah, just to the 100. So I moved a little bit. Oh. So it's going to go just to the 100, which will be negative 14. Negative 40 dB per decade. And then what's going to happen after that?
It's going to decrease by negative 60.
Negative 60, exactly. This negative 20 and this negative 40. So it's going to decrease by negative 60 until 1000. So at 1000, it's going to have negative 60 plus negative 14, negative 74. So 70 is this, and 74 is this. Negative 74. And that's going to be at 1000. Or to see that if it's different or not, but this line has the slope of negative 60 decibel per decade. It's going to reach to negative 74. And then what's going to happen?
Then it's going to decrease by negative 40.
Exactly. So this is increasing by positive 20. This is decreasing by negative 20. These two cancel each other. So the only thing will be left is negative 40. Then it's going to start decreasing by negative 40 again. So the slope of this line basically, which will be not as steep as negative 60.
Is there a point on the Bode plot where it's just too small a value to account for?
Well, these are all decibels. So as it is going down, your attenuation your signal is being attenuated a lot. So you can plot it based on what is the highest frequency in yours. So for example, our highest frequencies was 1000. So you can just plot it up to 10,000. That should be okay. Whatever the value coming out at that point.
Okay.
Yeah. So this is going to be, again, my freehand is not very good, but I think you got the idea. So the same thing we can plot using Bode function to see if it is the same. Let's see, what is our equation? Oops, saving, I guess. Come on, don't close on me without saving. So 200, let's go and plot that. So my new system is transfer function of numerator is 200, 200 times 1000, so 200 exponent 3. That's my numerator. And my denominator is, again, I'm going to use poly function to create the polynomial poly. And my roots are negative 10, negative 10, negative 10, negative 10, and negative 100. That should be squared bracket. So that's my polynomial. So Bode, that's my function, Bode of system. And That's my Bode plot. Let's see. So let's see how long it is going up to. So it's going up to 10,000. That's 1,000, that's 10,000. It's going up to 10,000 over here. And up to 10 to the power 1, it is 20 decibel. And then it starts dropping by 40 decibel. As you can see, the slope is, this slope is not as pronounced. Then it became a little bit, again, it's very hard to see. But this is negative 40 decibel, then this will be negative 60 decibel, and then it will become after 1,000.
The transfer function that was shown on MATLAB, it was the exponent of 3, right?
Let me see. Where is it? 200. So I have 200, then 200 times 1,000. So I put 200 exponent 3 times 1,000. And then in the denominator, I have 3 roots, negative 10, and 100, negative 100. So this is the transfer.
It's the expanded form.
Yeah. I mean, the graph is coming out to be the same, of course, that we draw. Our scale is just not, it adjusted the scale to show it properly. But you can see this line, although it's hard to observe, but you can see that the slope is changing from negative 40 to negative 60 back to negative 40 for this one. All right, so Bode plot is continued. We did this, so I did discuss with you if you have a square power or cube power. Again, if you have a square power or cube power, if it's zeros, then it's going to increase by 40 decibel per decade or 60 decibel per decade based upon what is the power. If it is a pole, it's going to decrease by negative 40 decibel per decade or negative 60 decibel per decade based on if it's power of 2, power of 3, power of 4 will be negative 80 decibel per decade. Single roots, of course, they will always increase either by 20 decibel or decrease by negative 20 decibel based on 0 and pole. And the constant function, of course, you just have to put whatever the value of that decibel for all frequencies. And then you're just going to add them together to get the Bode plot.